All right, we are now ready to prove the big theorem. And surprisingly, this big theorem comes from one more little theorem, which I will formulate. I guess I can't talk today. Now, the theorem says, let HA and HB be two cosets of H in G. Then there is a bijection HA to HB. Our proof of this relies on the following strategy. Strategy is assume, without loss of any generality, that A is equal to E. We often abbreviate without loss of generality like so, and what this means is that it is an additional assumption that was not written into the theorem. However, it does not hurt the theorem in any sense. In other words, you could think of it as like the world's babiest lemma. And at this stage in our math education, it's probably a good idea for me to explain where that little lemma is and what it says. But as you get better and better at proof writing, and also you do more proof reading, you will learn to spot these kinds of things yourself. So if A is equal to E, we have the coset HE, which are things of the form HE for H in H, but that's just H, right? HE is just equal to H. In other words, this is just the subgroup itself. That should make some amount of sense, like as a notation. The identity doesn't do anything. Okay, the next thing is if I have a bijection, H to HB, the theorem would also give me a bijection, H to HA. Since these are bijections, there is an inverse map this way. And so the inverse of this bijection gives me a bijection here, and then this bijection gives me a bijection here. And then the composition of two bijections is a bijection. And so the word bijection has lost all meaning to me now, but nevertheless, I have a bijection from HA to HB. So this is a simplifying assumption to just prove that every coset is in bijection with H itself. How does that go? Well, since H is a subgroup of G, I'm kind of a little bit closer to using my group theory brain, right? A general coset is just a set, but when I'm dealing with groups, I have multiplication. So let's make the function, and how about we call the function fancy B, cursive B of H, is H times B. Let's check that this is a bijection, also B per bijection. For injection, the answer is, we've seen this many times before. G is a group. Cancellation. If B of H1 equals B of H2, then that is H1B equals H2B, or H1 equals H2. Classic. On the other hand, for surjection, if I have some element, let's just call it HB in HB, unqualified, this is the fancy B of H by definition. And so everything in this coset is writable this way and therefore writable this way. So of course this map is a surjection. And that's it. We did it, right? I came up with the map. I proved it's a bijection. And believe it or not, we are ready for the big theorem now. This theorem is due to Lagrange. And what it says is that the order, sorry, I accidentally clicked a button and tabbed away. The order of any subgroup divides the order of any subgroup H, divides the order of G. And the proof of this is to essentially take the theorem from last time with the theorem from this time. So let's talk through how that works. So theorem 1 says we have a partition of G into cosets. Right? So G is equal to the sum of the size of, sorry, they are right cosets. Some number of cosets, right? We don't know how many cosets there are, but these are the distinct cosets. On the other hand, so this is theorem 1, right? That there is a partition and I can count them up. Theorem 2 says all of these things are equal. It's just the size of H itself. And so putting them together, the order of H divides G. The order of G. I guess that would be the best way to put it. All right. I have two consequences of this fact for you, which I think are helpful theorems. And since it's only been about, I don't know, 7 minutes so far, yep, coming up on 7 minutes, let's include those in this video, and then we can declare victory over chapter 13. So here's corollary number 1. If the order of G is a prime number P, in general, I'm going to try to reserve P for prime, G is isomorphic to Z mod PZ. In other words, there's only one group up to isomorphism of every prime order. The proof of this fact is as follows. Such groups, sorry, let me say it this way. Z mod PZ has only trivial subgroups. We can see that by direct inspection, right? We've got some experience looking at orders of elements in Z mod PZ. Well, G also has no meaningful subgroups. Because nothing divides the order except for one in itself. So you have the trivial group consisting of just the identity element and the whole group, and that's it. Therefore, take any G in G. We must have that G, the cyclic subgroup generated by G, is equal to G, the whole thing. Assuming that G is not the identity, that is. If G is the identity, then it's not true. But if G is any non-identity element, then the cyclic subgroup that it generates is the whole group. Well, if that's the case, G is a generator. So therefore, the isomorphism sending G to 1 in Z mod PZ is an isomorphism. All right, not so bad. We have a corollary 2, which I kind of just already used it, but let me spell it out for you as an explicit fact. The order of any element must divide the order of G itself. And the reason for this is just because given G in G, there's this cyclic subgroup, which is a subgroup. So since this is a subgroup by Lagrange, the size of this group has to divide the size of this group, but the order of G as an element is the same thing as the order of the cyclic group that G generates. And that's kind of the point. All right. And that gets us through our discussion of Lagrange's theorem. So as we always do, it's time for some practice problems. And I know we do things a little bit out of order in this chapter. And that's kind of because on one hand, I wanted chapters 12 and 13 to kind of go together. But on the other hand, I couldn't really think of any reasonable practice quiz questions on just chapter 12. So we're going to do our practice problems first this time. And then I'll give you the practice quiz on both chapters 12 and 13. And then we'll be done with this. It'll be time to wrap up.